Thank you again for this introduction. I have the pleasure to be the last presenter. And what I want to talk about is our hierarchical scheduling model for dynamic software systems. A very generic headline. And this work has been done in the scope of the Artus project. For the first, I want to say something a little bit more different than what you discussed, guys. So you were operating on the operating system, actually, and we implemented our stuff in the user space. But there are some similarities due to the dynamic server dimensioning stuff, which I want to present here now. So as I said, once again, we came from a more system-oriented direction and a different perspective, and had this project funded by the German Research Foundation, which objective can be summarized very generally as provide an adaptive resource management framework for a platform supporting a dynamic set of applications with unknown and fluctuating resource demands during runtime, which further have soft-real-time requirements. So,
well, what definition of soft-real-time?
Yeah, actually not hard real-time.
But that's a lot.
I mean, to what do you exactly relate?
So there are various definitions of soft-real-time. One of them is bounded tardiness. I forgot the other one. Jim mentioned a few. There is statistical limit on matching deadlines. There is.
Okay, so actually we assume that we tolerate deadlines, but we want to minimize them. It's very generic. So we have our focus kept on more other parts, which I hope that I will show right now. So we tried, of course, to identify first requirements for this. We assume that actually we have a system where applications can dynamically depart and arrive on the system, and since they are unknown during runtime, actually the execution times of their tasks and their exact resource demands have to be measured and estimated. And they're, of course, platform specific and must be initially calibrated for the applications. And they can also jitter, so it's a little bit interactive thing here. So such a system, what we identified first is very general actually, but we came up to our hierarchical scaling model with this. We need a kind of permission control in order to restrict the amount of applications or active applications in the system in the case of bottlenecks. And the other side, we need a kind of dynamic monitoring of application costs and also resource reservations in order to isolate applications from each other, and also in case of misbehavior to be able to enforce these reservations. And furthermore, we need a kind of overload management strategy. So we know from the literature that there are different types how to manage overload. For example, we could use elastic scaling, we could use job skipping, stuff like this. Even Professor Butato suggested that it's possible also to degrade the quality of different tasks and applications in order to fit them to certain resource amounts. And this is actually what we decided for based on different operation modes of the applications, where we just assume very generally that a specific operation mode is an application configuration in which a specific utility is generated under the condition of a certain resource amount, very generic. So in this case, we need a kind of central control mechanisms which actually monitors the operation modes of the different applications, or the execution in particular operation modes, decides about the optimal configuration of these operation modes of the applications, and also switched applications, of course, there during runtime. And we also required that we should be able to prioritize the applications, which means that applications which have a higher priority should also possibly run in higher modes. And we also expect that mode switches of the applications imply costs for reconfiguration and data adjustment, and those should be omitted and minimized in our system as far as possible. So we would like to keep the system very constant and very stable in one particular configuration, and redistribute the resources only if this is necessary. So such a resource management system could be, of course, integrated, for example, within an operating system. As I said, we did not this. We decided to integrate it into a middleware, just because of the assumption that it would be more generic and fit a broader range of different devices and platforms, which is a very naive assumption back those days. So from these requirements, actually, we first extracted a particular real-time-based application model, in which we actually assume that each application consists of a set of periodic tasks. So we focused first here on periodic tasks with arbitrary deadlines, which means that the deadlines are less or equal to their periods, not larger because of implementation issues with this model. And they have different modes, these tasks, which are here depicted as different versions, which are dynamically selected during runtime, with particular periods and deadlines for each version, and the costs are actually estimated during runtime, measured and estimated during runtime. And we assume, of course, that these modes somehow provide different quality under the assumption of different resource demands. And then a concrete application mode is basically a configuration of these task modes, like in this example. It's just a selection of these tasks modes, and an application, of course, can have several such configurations and modes. And each application mode has a certain processor demand and a utility. The processor demand is the cumulative measured demand of the application's tasks in their appropriate modes, and the utility of each mode is provided as a numerical value by application developers, which is then normalized within our system, meaning that the highest mode has 100% utility provided with this application, and the lower modes have different percentage, which is normalized to this. So we generally assume that here application modes or a higher application quality would require more resources, which does not have to be actually in the reality. So our system is nevertheless capable to couple with such configurations where a higher mode doesn't have really a higher resource demand, but maybe a lower. Nevertheless, this monotony is not required by our system. It will nevertheless select the optimal mode configuration. We introduced a zero mode, yes, which means that the application is currently stopped or suspended. The tasks are suspended. For what reason? We wanted to ensure that an optimal resource distribution within the system always exists. And on the other side, this implements a kind of priority controlled admission control for the application. So it's decided which application would run in mode 0, depending on the priorities of the applications, their actual resource demands, and so on. Okay, what is the scheduling problem then? We have a variable set of applications and internal tasks with different operation modes and fluctuating resource demands. These are the modes of different applications, for example. And the objective of our resource control mechanism is to select an active configuration of application modes, and thereby to maximize the overall system utility according to the resource demands of the applications and their tasks, with respect to the overall available resources, with respect to user preferences, and finally to prove the feasibility of all application tasks. And as you can imagine, especially the last point is really a little bit hard, because we have now here a huge amount of different configuration possibilities. So traditional approach would be here, for example, to check the feasibility for all task mode combinations here of the different applications, and to select the best one, which actually accords to the application mode definitions. But you can imagine that if we have even tasks with deadlines less or equal in periods, this complexity for this feasibility test will escalate here. And still the question remains when exactly and how often to perform these feasibility tests during runtime. For example, if the average cost of each task varies, so this would, of course, mean that we should constantly perform feasibility tests, redistribute the resources, maybe decide for different operating modes for the applications, and this is actually what we wanted to omit. And our idea was here to perform the feasibility tests only when and where needed in the system, and we followed this idea to this hierarchical scheduling model, which actually follows the abstractions of tasks at the lowest level and applications on a middle level and a third level, which is actually the optimization of the application modes. And thereby, the application behavior is abstracted on each level, forwarded to the next higher level in a kind like a cascaded control system, so that on the top level only global configuration decisions about application modes are met. So just a short overview how this functions. On the task level, we have tasks.
You mentioned average utilization or average cost. Do you then also use stochastical analysis to
Stochastical analysis
for the access control and the deadlines?
I will come to this in a minute. Okay. So maybe this would answer the question, and we can come back to this question. A short overview of how this functions. At the task level, we have the task scheduler, one per application, and they control the execution of the tasks with release deadline first, which makes things easier. We'll talk just a little bit about this. And they approximate the behavior of the task with respect to their measured deadline. measured cost of the airlines. And as long as these approximations here remain accurate, no state update is propagated to the upper levels, and the system remains feasible. And only if a task violates its approximation limits here, a new task cost estimation is computed and delivered to the application level, and thereby the resource demand of the whole application has to be updated eventually. And here, for this, a local feasibility analysis has been performed, leading to a new capacity and bandwidth allocation for this server. I will come later to this, that we encapsulated this in servers.
So the squiggle is the change in utilization. What do you use for access control? The maximum value or the average value of your wiggle?
So on the lowest task level, the estimates, this should actually answer the question. We use the average, the exponentially smoothed average, and here's the double standard deviation for a time period of n task periods. Okay, so this somehow enables a kind of safety buffer for guaranteed resources for the tasks. So if you take a regard here to the actually to the confidence intervals of the standard or standardized normal distribution at 2 sigma. This is actually what happens at 2 sigma. This means that since we compute the standard deviation in a time window of n task periods, we approximate task behavior from the immediate past of n task periods with a certain quality here, which can be controlled by this factor actually. So the upper bound here of a safety buffer is the actual cost estimate of the task, and this, the lower bound, avoids the system from constant over-provisioning. Okay, the strategy is like this. We have rate-based checks and updates of these buffers. For example, what is interesting here is that we look at the mean values, which are constantly computed. This takes actually a constant effort in the system, are violating the actual approximation buffers. And if this is the case, we have, of course, to establish a new buffer here with a new cost estimate for the task. And only then we would forward this information to the next higher level. And this can be done rate-based. For example, if the tasks do not suffer from deadline, this is what we could do it, for example, with a hyperperiod of a certain application, hyperperiod of the tasks. Since here the approximation seems to be somehow accurate now, and if the tasks do not suffer from deadline misses, then we would like to omit costs for this computations, and this will configure it to lessen the reconfiguration probability. And on the other side, if we have tasks suffering from deadline misses, we would like to approximate them in a better way, which might lead the system to a higher reconfiguration probability.
Right. So you are familiar with the work from Bauer? So how would you pronounce UNC?
I say Bauer.
Yeah. So he did statistical task model analysis, and I always only look at the end result because the intermediate stuff just. But yeah, it's a very good paper that deals with such types of tasks that have variable and then standard deviations in their task parameters.
Okay. So
we've been investigating a similar model in the Feasibility project. So I can hand you over a paper from 2010 where we basically define a whole software architecture dealing with tasks having a finite set of possible modes. In each mode, you can define different scheduling parameters, so different requirements, as well as different target, for example, percentage of deadline misses. So you could have a mode in which you really want 100%, or another mode in which you're fine with 90% deadline misses. That would correspond to degrading the QoS. And you can associate the QoS level to this mode, so that when you build this specification for the task through the API, you can say, okay, in this mode, the application is running 100%. In this other mode, it's running 95% of quality, and so with the other ones. And then there's actually an optimization framework that decides which application modes to use for each task in a distributed embedded systems.
But for each task? actually. And what I saw about the
that
Fresco,
for each task, and also it decides which power frequency switching mode to use. So in the paper, we also address, you know, a finite number of possible frequencies with different associated power modes. So in the optimization framework, you had some tunable weights, which you could say the easy things are like, you know, I want maximum power savings. Then the optimizer would actually, you know, get the, you know, it will slow down the tasks, or anyway, it will reduce the application modes. Or you could say maximum performance. So if you give more weight to the application performance QoS, then the application would try to stay at higher QoS modes, and also the platform would be pushed towards more power-consuming states. And then you might have intermediate, you know, with these tunable weights, you can actually change it. So maybe I can hand you over those.
I tried to find a little bit more information about the Fresco.
Yeah,
project. I read a little bit of the deliverables, and they were a little bit blurry, you know, the definition of first of the task model, second of the, what is there? Is there kind of approximation of the task?
There's a whole set of open source software components published, so I can hand you over to software, which is very common. So we have all the API, which is, I think the API is well documented with Oxygen and stuff. I mean, basically, because implemented based on the old scheduler. I mean, you know the keyword. I cannot pronounce it because the price here. Somebody else said the old scheduler, the old reservation-based scheduler for single processors on Linux. So, but there's the API. There's, I think, one problem about Fresco is that I think the coordinator put down the website now because it's already, I mean, it was from the 6th framework program, F36. So it's already 7, 8 years ago or something. So I'm not sure where we have the public deliverables, if there's any place where we still have the public deliverables. But there are the papers where there are different cuts on the framework. I think
you didn't try to scale a couple of tasks directly bounded by one CBS server. So what I think that you did is to try to calibrate the costs or the resources for each task during runtime on a task-based version, so that they have a very flat model, actually. Or am I assuming wrong?
In the model, there was, in that architecture, we were supporting multi-threaded components if you wanted. In the prototype and demo that we built in the end of the project, we were using single-threaded tasks. That was multimedia playback. I mean, that's what was multimedia. So classical example was an M player on a laptop. You start a player, and it goes where it's a full resolution, full filtering options. Then you start the second player, and it's again full. Then you start the third one, and basically they degrade gracefully. So like dynamically, they decide to switch to a different mode. So you would see that because we disabled some, can't remember, there was some post-processing filtering after the impact decoding. So it would, they dynamically switch to lower operating modes to, you know,
task-based,
but you know, still being reactive. So like the end player will still keep the frame rate without dropping frames. Instead, with the original Linux platform, you start the end players with all the options on, and when you start the third player, just they all start, you know, everything blocks.
Of course.
You know.
But the decision of the modes, actually, or what I described as modes on the task level, is based, you have a kind of optimization going through all the variations of all the tasks. And with different quality levels of the tasks, decides completely for the whole task set.
Yes, that's also what we used. There was this optimizer that was deciding for the whole. So it was operating on one hand on the application modes, and on the other hand, it was operating on the power knobs that you had on the platform, like CPU frequency. And that's why I think in the demo we had even the light of the screen light brightness. And we had an optimizer that was based on, let's say, getting the optimum configuration for the platform, which was compute intensive, implemented through gRPK. So that's something basically we've done in user space with the daemon that was re-optimizing things. And then we made a simple, just a simple heuristic that was running like 1,000 times faster and was getting enough good solution, but that's easy for writing a paper. In a lab experiment, it's easy. So in reality, but for a research project, that was quite impressive in the end. I mean, in the end, in a few milliseconds calculations, you could optimize this. So it was not really such a heavy thing, this optimization, but it all depends on the size of the system. So like if you try to do that on 10 nodes with 10 tasks per node, then it becomes heavy.
So what we actually then did is that we encapsulated the tasks here and console memory servers, and what we had to trade on the upper level, on the optimization level, was just the bandwidth. So it's a pure knapsack, really quickly solvable knapsack. We have here an implementation. Okay, I had here a little bit about the relation of server dimensioning and multiple tasks. So we use actually here the minimal, the server period, the period of the task with a minimal task period, and then the capacity of the server is actually based on the feasibility analysis, which is done on demand with the actual task cost estimations. What we used here is a very simple algorithm for the feasibility analysis. This is the one by Varua et al. And as you know, there is this approximation tangent of tasks, DBF, and we take here, because we're using EDF, we take here the value for the hyperperiod. We are actually enacting here the property of EDF that as long as the task cost estimation does not change, the activation sequence remains equal. So we are performing this feasibility analysis for the hyperperiod, and then we are normalizing this with the chosen task period, which actually means that, okay, I will skip this. That if you consider, for example, a small transformation of this formula here, if we have deadlines equal to the periods, then this capacity is made up purely of the utilization of the task, which makes sense, and for tasks with deadlines which have distance between their deadlines and their periods, there is an additional amount of capacity which is required, of course, to serve the tasks with a higher processing amount of the tasks. And this is actually the server dimensioning which we established here in order to guarantee that the tasks remain feasible within the server. So actually, we have not identified any reason why multiple tasks could not be handled by one CBS. The CBS rules do not restrict this. We should extend maybe the server with an internal queue or something like an internal run queue, and which can be ordered due to a particular scheduling strategy, but nevertheless, the server would be capable to host multiple tasks. And this is just about the dimensioning here, how to, yes, these are the terms which determine then the case for less or equal than T.
So then we use a CBS for isolation, because we cannot ever trust user space to be well behaved. We don't want a misbehaving application to influence the behavior of another.
Yes.
So if somebody reverts to being a while one loop, we want the other applications to still get their actual time. And if you shove multiple applications inside one CBS server, you lose that.
Well, you still trust the user space at in a peer with the runtime event required for that task. So certain kind of trust into the user space you always have to pay.
Well, yeah, but I mean, if you, but they won't get anything more than they ask for. And so if once we've given them the guarantee, the resource, they will not be able to adversely affect the others.
So my general view is there are many of these words. It is not only so there are other words. So the point is that now we have really sophisticated mechanisms in kernel space that they are advanced and really precise on getting these things. But these approaches are useful because they start from the other way around. So they start from applications and they put into the mix the idea that there is a runtime that is trustable in user space. And this runtime knows about application needs. And is the guy that can feed information into the shaper to use properly this kind of mechanism. We are completely missing this view right now.
Actually, this was the problem.
That only works as long as you have one middleware.
Sure.
If you put two of them in one system, you screw
No,
again.
but if you look at Android, we have one. If you look at Chrome OS laptops, we have one. If you look at Kubernetes, we have one.
If you look at people that try to consolidate legacy systems, you have many. And
it's not for legacy systems, it's really for new systems. So that's, in my view, the goodness of these works is that they are a new view, where we have to start considering that there are user space that are knowledgeable.
Like, what about running, say, Android applications on Chrome, which people do? Running with Android stack on the inside of Chrome. Like
You can have probably a delegation model in which Chrome gives some kind of resources to the Android applications that are managed. It's just that you have to trust someone in user space. And this is something that should be there. Also, if you use Deadline and whatever we want, there should be some trust in user space that someone doesn't abuse whatever mechanism we are using.
There's so much history of abuse in user space.
But yeah, at the same time, that's why maybe platforms like Android are more successful than desktop for certain kind of application. Because there is something which is.
I guess the point is that at a level we give.
You only need to have one bug and say surface flinger and your entire stack is gone.
Well, surface flinger is under control of the integrator. It would never be bugged such much without noticing by someone.
Because there are never any security exploits in Android.
Yeah, there are bugs in kernel space.
Yeah, I know, it's good.
But look, when you talked, for example, about this problem here, there was also the problem of trying to estimate or actually to what kind of guarantees could we provide here to these tasks which are running in this queue. If we have no information from the user space, at least a kind of progress information. The task says, well, you know, I get resources, I'm performing well, so for me it's not quite good.
Yeah,
this is
so
what we
for
get,
the
of course, with the real-time
administrator,
model.
Configure the C group, which is the interface that allows you to specify stuff. So whoever creates a C group sets limits on that. And
but from when does he know, from where does he know what, as Luca Benias did it, for example, I have here a period, a cost and a period. Where do I know it from?
whoever designed the application must have some clue. Or, I mean, if you're the legacy operator, I mean, you've run the thing, you can run it and observe it and then see what it does. It's just a configuration issue. We don't care. Let them sort it out.
And you're sure that then you have, or these guys are always reserving the right bandwidth?
No, but that's their problem, isn't it?
I don't know. On the other side, we want to share resources in order to omit bottlenecks, like things like grab and cache.
I mean, you can keep stacking on middlewares. At some point, people will end up in the situation where one set of applications written against one set of middleware and another set of applications written against another set of middleware need to live on one system. I've seen this. It happens.
Yeah,
but that's broken.
No, it's life.
It's life.
No, it's just trying to make something working, maybe because you want to use legacy solutions. But the point is that we should try to set a message about how things should evolve and should be designed in the future, right? So there should be one entity in user space that is trustable. Or if there are more, they have to be designed.
It's just not.
You're denying reality. I mean, that's all nice on the wish list, but it's not going to happen.
I think it's already happening.
In some spaces, it's happening because you can't control the space.
Mobile phone.
Yeah, because you can't control what's running on the phone.
Okay, but there are more mobile phones than desktops around, so it's not few systems.
And but this is an environment where we actually can control what's running.
Sure.
But then once you leave that environment, reality starts.
Yes.
Yes.
And very effective.
So
Very small.
you can say this is the way how the middleware on my phone works.
Mm-hmm.
And you can integrate all the magic things into that middleware. So fine. But then there is a world outside of Android, really.
Exactly, and what we are missing is something which is generic enough and is not Android, but still everybody believes that it's a trustable middleware that can be something on top of it.
Then go out and look at what real-time, the various applications and real-time systems do. They are so totally different in terms of requirements and applications. You won't find a malware where they all fit in.
That requires some kind of analysis. I think it's why universities can play a role trying to suggest these kind of trends. That's research at the end.
Yeah, but on the other hand, you also have to live with the fact that if you go in the industrial application space, you have to live with legacy code, which is started 20 years ago.
It's not all these kind of European projects. They are backed up by industrial applications that range from aerospace application, automotive application.
Yeah. I know all the research is nice and shiny, and then you go out into the companies and look at the actual code, and it's based on 20 years old shit. And nobody's going to change it because nobody can re-implement it because it's way too expensive to do so.
There are some companies that try to be leading edge and use this kind of approach.
For certain new things, yes.
Sure, yeah.
But there is that whole look at the whole application space out there. Who's going to rewrite Fortran math libraries in some other language? Nobody.
No, yeah.
So
but it can
same
be
thing.
They are changing the execution model. MATLAB as for acceleration, maybe for OpenCL, and this quite recently.
Sure, but
they change it.
Sure, you can't. There are changes out there, but you still have to deal with the fact there is a very large amount of legacy style code out there which needs to be served.
Yeah, okay. And
so we have to deal with that and not break it.
Sure.
That's the important part.
But that's understandable, and it's okay. Still, it should not inhibit to look at this new.
No, I'm not saying you shouldn't look there.
Yeah.
But you have to be aware that there are dragons out there, and so I doubt that on anything else which is not as restricted as a phone, people will start to malwares. Because there is no single malware which will fit 25 requirements of 25 different things in one go. No, it's not going to happen. I severely doubt it. I mean, they tried it with Java, and look
but
very
Java
good.
is nothing compared to that.
Yes.
There is nothing of this concept. So it's
I know.
It's about everything else. Java, portability, and other stuff. So it's not really anything related.
Yeah, but they tried it to implement a middleware on top of Java as well. And now go out and look how many middlewares there are around. And if you look at big
Oh,
Java,
that's only the recent stuff. I mean, there's middleware since the 70s.
yeah, sure. And then you go and look at any decent big Java installations, and you run 5 middlewares on top of Java, because every implementer uses a different one because this one is better than the other.
Yeah, there was many operating system before Linux, and now we have Linux, just because we trusted that it was the way to go. I think that if we define something we trust is the way to go, we can achieve a single middleware.
There's still a lot of people not using that.
Yeah, well, many people are using it.
Yes, but there's still a rather big market for non-Linux based stuff.
Yeah,
I mean,
but
Can I,
Doesn't matter because
do you mind if I propose to maybe we?
yeah, sure.
No,
We
Yeah,
should
sorry.
finish
we are only-
funding
Okay.
offline and maybe just.
I'm not sure
kind of
if I can tell you
presentation.
anything interesting anymore, because as you said, everything has been developed in a different way. So we had maybe an alternative type of system where we focused on how to use the CBS, how to dimension them in order to serve the tasks with deadlines less or equal than in periods. When to perform the feasibility analysis, actually when we break out of the approximation buffers of the task. And this led to a system which somehow tends to perform feasibility analysis only locally for particular applications and to distribute the resources accordingly. So I had here this knapsack solution for the decision of the operation modes. It depends, of course, on the kind of resource resolution of the system. This is maybe something which is interesting because how we represent the bandwidth, the 1 case. So it could be approximated with a different range of integer steps, for example, and this, of course, influences the complexity of our knapsack algorithm here, because we iterate over the different resource configurations and try to optimize this to the particular application mode selections for the particular resource. So
maybe I missed a piece. So in terms of scheduler, you said you are using multiple tasks inside the same reservation.
Yes.
But are you doing only theoretical analysis here, or did you implement that? Did you work with the real implementation of?
We implemented it. Yeah, we used, in this case, we wanted to be more abstract and even use the real-time Java. So you blame me, please. But nevertheless, we wanted to have a kind of framework for loadable applications, for loadable and dynamically portable applications, for example, as using a phone. Yeah. So nevertheless, we used here the Jamaica VM. Jamaica VM is a native compiler, ahead of time native compiler. So it strips down all the RTSJ environment only to the needed classes, needed functions, and binds everything to a native executable.
In terms of scheduling, in terms of scheduling in the kernel, what did you use?
SketchPeople.
Oh, so it's based on.
So we had EDF and we had to shift. One interesting point is that. One interesting point is maybe which I want to come
you
later.
Also CBS, right?
Yeah. I showed you CBS here. Yes. Internally running EDF, the CBS are running on top of SketchPeople. So how? With priority shifting.
But you implemented the scheduler, or you worked with SketDeadline, or?
No, we implemented it direct on fixed priority based scheduling, which is mapped to RTSJ. Okay, let me just come to this.
Yeah, maybe I missed that. Okay, the architecture. Thanks.
Linux preempt RT, RTSJ Jamaica VM. Okay, something to load components, to wire applications, to control their dependencies, and then our framework. So our scheduler here, the Jamaica VM directly maps to real-time threads to SketPeople. We can control the priority range of SketPeople, and as I said, it's a kind of native compiler. So everything is compiled to native, for native binary, which we can execute then on a particular device. One thing which I want to come back here is what happens. Okay, this is the performance of the knapsack algorithm. I know. Okay, it's pretty clear that the scale is linearly in each dimension. Okay, but one thing which is more interesting is that here, what would happen if we have one task bursting out of its approximation limits in such a kind of system? The cost estimate for the task is established here. Then we perform feasibility analysis for the particular application, extract the new capacity and bandwidth for the constant bandwidth server. Move it forward to the optimization component, which now has to check if we are over a certain utilization ratio of the system, and then turns on the knapsack algorithm to compute the optimal mode configuration. So one burst of one task can reconfigure the whole system. And the question is, how behaves the system when we have cyclically bursting tasks?
When you have
cyclically bursting tasks. So I want to come to such an example here. So let's skip all this stuff. This is the scheduling priority shifting on the task level and on the CBS level. I can come back to this if you want, if it's interesting. But I think we used here the works of Zarzalidis and Wellings, which also proposed such a custom scheduling mechanism for the RTSJ specification, or based on fixed priority-based scheduling. Do you know how this functions?
Yes, no. But the cycles, they don't have a shared period, I think. So at some point, you get all the maximums lined up.
For this EDF scheduling based on fixed priority scheduling?
Well, not for the. I was still thinking of the previous slide where you had applications that had a cyclic mode change.
Okay, let me come to this one. This is more interesting. For this, what to say is that for this, just is that we use this priority shifting to shift the tasks between three different priority levels each time before they're suspended and when they are released. So they're suspended always a scheduling priority. They can perform a local rescheduling here. We could use, for example, EDF here. There's only one active task always selected in the other preempted. Okay, and that based on fixed priority scheduling, this is accomplishable. We can emulate kind of EDF.
The switching is done from a user space.
From the user space. Exactly.
Like system calls.
Yeah. Okay. The same for the CBS scheduling. So we have 3 instances when to schedule the CBS to shift them between different priority bands. The 3 instances and when we change the scheduling deadline of the CBS. This is the server activation, the server deactivation, the budget depletion. And since we run here on RTSJ, we had the problems that we did not have enough information from the RTSJ processing groups, use processing groups, which are actually meant to implement custom server-based mechanism. But they are not offering us the opportunity to replenish the budget when we want. They're doing it each time at the beginning of server period, which is more well suited for developer services.
You can try to play with the hierarchical CBS patch and see what happens.
This?
You can try to play with the hierarchical CBS patch and see what happens.
He wants EDF anyway, so he can just use get deadline directly.
But the sched deadline is making a kind of global deadline based CBS scheduling for the tasks.
Also to push multiple tasks in the system, right?
Yeah.
So that's why I was saying, yeah, maybe you can play with this hierarchical CBS patch. Just it's a matter of building a native interface for Java by which you set up the C loops and all the stuff.
This is a good idea.
Maybe you can play.
Okay.
If you need help, just if you're gonna crash from the patch, like I said.
This is an example of a bursting task. So we have here a really measured task. This is this jittering stuff here, cyclically bursting between 2 values, Cmax and Cnopp. And it has that a period of 200 milliseconds, costs 50 milliseconds, the maximal cost for the burst length 90, where the jitter window of 20% around the target value, where the deadline equal to the period here, just because we are relating some other case here. Burst period and burst duration in terms of task periods. And what we see here is that the safety buffer, actually, which is this green line, so we have here the estimated, the exponentially smoothed values of the task, measured costs. We have here the standard deviation, which is computed only if the safety buffer was updated, because it's over the time window of 20 or how many time periods, task periods. And what we see here is that at some point, this jitter of the task or this burst is considered as jitter of the task and automatically covered up by the standard deviation. So this buffer gets big and almost could, in this example, approximates the jittering cost and the bursting cost, cyclical bursting cost of the task. So this is on because the burst period remains constant and the burst strength remains constant. So our idea was here, we used here half burst duration window for sigma computation, for standard deviation computation. If we would shrink this window, of course, we would get cyclical configurations, periodical updates of the cost of the task. And on the other side, if we have bigger window looking into the past, we would have a higher over provisioning here. So the idea is how to control this dynamically. And we were currently working on such a dynamic adoption of this sigma window going over the measured costs in order to, on the one side, do not too much over provisioning, but on the other side to approximate the cyclical bursting task. Okay. Okay, this was about the buffer. Of course, these resources could be shared with cache or graph or something, and also used to serve such small outliers beyond the current estimate of the task costs. But this is nothing which I think is new. It has been discussed already. I don't want to go once again more into the details, but leave open some potential for discussion. Let's skip this part and directly discuss if there is something more interesting, because as far as I understood, there are already systems implementing related stuff. Our contribution, I think, was in the dimensioning of the server, the approximation of the tasks, and also this dynamical control of the windows, controlling the over-provisioning versus the accurate approximation of cyclical versus tasks. So are there any further questions? Or
can you mention an example of real applications that's being used or implemented?
We had a video on demand example, a video on demand example. So we had I think I should have you some slides. Very basic. Okay, just don't consider it. So we have here, and there's from German. I did not transform it into English. But however, there is a receiver task and a visualizer task, receiving a video with a particular quality. So the different application modes were realized as different frame rates, different frame quality, and stuff like this. And these tasks were synchronized with the frame rate, of course. And when here a bottleneck occurs, then the receiver, the client actually of the video signal, could request a lower or actually a higher, if there are select resources, quality of the video. So we start the original video and the target video here and compare them with the PSNR comparison here in order to see what is better. If we have a bottleneck here and deadline misses, and in the case of deadline misses, we have a signal corruption. So for this particular frames, we store even black frames here because we are missing the information. Or if we degrade actually to a lower level and request a particular lower quality for this transient overload.
But that's still a single application, right?
And then we started the test application generating a bottleneck, so forcing this application to degrade into a lower mode. And then we, what we got is, of course, that we cannot control where the deadline misses occur. So they occurred in both applications. And what we got then, okay, we run this test with degradation capabilities of our system and without. So we assume that with degradation capabilities, we will have not so many deadline misses, and we generating better throughout quality of the video on the PSNL.
Sorry, are you talking about video on demand or live streaming?
It was actually a requested video, which is
So
transcoded.
why is it a real-time application at all?
Please?
Why is it a real-time at all? So if you are doing video on demand, you have bad connection or bad quality, you just increase the buffering, you don't have real-time requirements for the transmission of the video.
No, but we have the problem if the resources are not enough for these tasks here to complete into the scope of their periods and values. You know? So we're starting in another application running at the client system, which steals the resources for the periodic
so
tasks.
you're talking about overloading in the client.
Overloading the client, actually. And the network in between was completely isolated in order not to have the effect of the network. Okay? Is it clear?
Multiple cameras in a smart car nowadays.
Yeah, that's
you want to reproduce rear mirrors, center mirror, you want to
streaming,
reshuffle
not
it.
video on demand.
Yeah, it's like a streaming.
Okay, live streaming, I agree.
Yeah. So this is the kind of
Video on
scenario. You have
demand.
multiple applications running concurrently on limited resources, and you have to shuffle resources, and it's not only CPU
For live, I agree.
but GPU.
Why video on
These are
demand?
industrial applications that can be targeted.
For live streaming, I agree. The video on demand.
We want to do a comparison between the original video and the target video, which was actually received at the receiver side, and the quality actually of this target video. You know, actually the target or what was the result of the degradational mechanisms of our system. So therefore video on demand, because there was an original video which was transcoded here in real time, set over the network, and the client was put into bottleneck, not capable to serve the periods which are required by the frame rate of the video, and the costs which are established, of course, because of the quality of the frames. And then we compared them. So what we saw that the average PSNR here without degradation was even better than without degradational mechanisms. But why? Because we could not control here where the deadline misses occur. So they occurred, of course, in the application which goes to bottleneck, and not in our video on demand application. And on the other side, it also depends on the definition of the modes of the application. So we had maybe here a mode which was defined in a way that the quality of the video at all was not so good with respect to the original video. But for the points where we had the particular bottlenecks, so this is the average of all values below 99 dB, which we just measured until 99 dB, because from then on we assume that they're equal. Okay. So here we see that for the case where actually the bottleneck has occurred, the quality was degraded a lot because, of course, we have the corruption of the signal in this case, and with our mechanism we could establish some kind of acceptable quality for this partial temporary bottleneck, transient bottleneck. So this is a system which actually during runtime measures the costs and makes these decisions and tries to take the best decision about the quality and keep the tasks still feasible. Okay. Good, thank you for your attention.
Thank you.